In this lesson, we will discuss the polar representation of complex numbers. We have already talked about representing a complex number x plus iy as a point and rectangular coordinates x comma y, where x is the real part of z and y is the imaginary part of z. So we're going to let r and theta be the polar coordinates of this point, where r is going to be the length of this vector representing x comma y, and theta is going to be the angle measured from the real axis up to the vector measured in the counterclockwise fashion. So these two numbers, r and theta, are the polar coordinates for the point xy. xy is the point corresponding to the complex number z, which is x plus iy. The angle measure is measured in radians. So if we look at the relationship between x and y and r and theta, we can see that if I create a right triangle where the vector is the hypotenuse, then the height y of this point is given by the formula r sine of theta, and the rectangular coordinate x is given by r cosine of theta. So if x equals r cosine of theta and y equals r sine of theta and z is x plus iy, then that tells us that we can write z in the form r cosine of theta plus I times r sine of theta. And if I factor out an r from both terms, we get the polar form of the complex number z. So z is written as r times the quantity cosine of theta plus I sine of theta. And we'll see in a minute we'll have an alternate form called the exponential form, where we're going to rewrite cosine of theta plus I sine of theta. So we're going to assume that r is positive, since the angle theta would be undefined for the complex number 0. A couple of quick notes on polar coordinates. R is equal to the absolute value of z, or the length of the vector from the origin to z. We already know that's equal to the square root of x squared plus y squared. And we can find the angle theta from the identity tangent of theta equals y over x. Theta is called the argument of z, and it's going to be denoted by arg of z. And we make a distinction between lowercase and capital A for the argument of z, because there's an infinite number of values for lowercase arg of z, and they each differ by 2 pi radians. So we're going to single out a single value of the argument of z and call it the principal value of argument of z. And we're going to denote this by a capital A. On argument of z, so by capital A, Rg of z. And this is going to be the angle measure that is between negative pi radians and pi radians. So capital ARG, the principal value of argument of z, is the value such that argument of z is going to be greater than negative pi and less than or equal to pi. So for example, when we have a negative real number on the complex plane, we'll measure the principal value of its argument from the positive real axis, open the angle up, and so we would get an angle of pi for the principal value of any negative real number. So when z is a negative real number, we want the principal value of the argument of z to be pi. So we don't write it as negative pi. And so now we think of lowercase arg, lowercase argument of z, to be a set of any of the angle representatives in polar coordinates for the complex number z. So we can think of it as the set capital ARG of z, the principal value, plus any integer multiple of 2 pi. So plus 2 pi n, where n is an integer. Now let's look at an example. Let's find the principal value of the argument of z for the complex number z equals 2i divided by -1 minus I. Well, in order to find the principal value, I'm going to write this in rectangular coordinates first. I'm going to multiply the numerator and denominator by the conjugate of the denominator, -1 plus I. And in the numerator, I will get -2 minus 2i. In the denominator, -1 squared is 1, and -I squared is 1, so I get 2 in the denominator. And when I cancel a common factor of 2, I get -1 minus I for the rectangular coordinates of z. So let's look at this complex number in the complex plane. So -1 minus I, if I look at the point -1 in the complex plane, this would represent -1 minus I. So if we measured the angle in polar coordinate angle theta from the positive real axis in the counterclockwise direction, we would get an angle of 5 pi over 4. But this angle is not in the range from -pi to +pi. So you could take this argument of z and subtract pi subtract 2 pi to get the principal value. Or we could measure from the positive real axis in the negative direction and get an angle measure of negative 3 pi over 4. And this would be equal to the principal value of z. So the principal value of 2i over negative 1 minus I equals negative 3 pi over 4. Let's do the same thing for the pure imaginary number for I. Well, on the coordinate plane, 4i lies on the imaginary axis. This would represent 4i. And so if we measured the polar angle theta from the positive axis, we would get an angle of pi over 2. So we see that the principal value of the argument of 4i would be pi over 2. Now we're going to develop another representation of the complex number z in what we call exponential form. So let's first recall a couple facts about power series from calculus. So from calculus 2, we might see the following power series representations. For any real number x, we have that the exponential function e to the x can be written as the power series sum n equals 0 to infinity x to the n over n factorial. And this series converges everywhere, so this power series is valid for all real numbers x. We also have the power series representation for the trig functions cosine and sine. Cosine of x is equal to the power series n equals 0 to infinity, negative 1 to the n, x to the 2n divided by 2n factorial. And sine has power series representation n equals 0 to infinity, negative 1 to the n, x to the 2n plus 1 over 2n plus 1 factorial. Note that an alternate expression for e to the x is exp parentheses of x. When we have complicated expressions in the exponent, it's often easier to write exp of x instead of e to the x. So using these three power series representations, we're going to substitute in I theta for x in the power series for e to the x. So then we see that e to the I theta is going to be equal to this power series from n equals 0 to infinity of I theta to the power n over n factorial. And I'm going to break this power series up into the even and the odd powers of n. So I'm going to write this as the sum n equals 0 to infinity, where now I'm just going to single out the even exponents, so it's going to be I to the 2n times theta to the 2n over 2n factorial. And I'm going to add this to the series n equals 0 to infinity, I to the 2n plus 1 times theta to the 2n plus 1 all over 2n plus 1 factorial. And then I'm going to use the fact that I squared is equal to -1 to write this sum equals 0 to infinity, -1 to the n times theta to the 2n over 2n factorial. And we recognize this series as cosine of theta. And before I rewrite I to the 2n as -1 to the n, I'm going to factor out a factor of I from the numerator of the second series. Then I can write I to the 2n as -1 to the n, theta to the 2n plus 1 all over 2n plus 1 factorial. And we see that this equals cosine of theta plus I sine of theta. So we see that we have the famous identity, which we call Eulers Formula, which will help us write another representation of complex numbers in exponential form. So Eulers Formula states that e to the I theta equals cosine of theta plus I sine of theta. So now using Euler's formula, we can represent any non-zero complex number z equal x plus iy. We wrote it in polar form as r times the quantity cosine of theta plus I sine of theta. And we see now we can represent this as r times e to the I theta. And so this form of z is called exponential form. So z equals r times e to the I theta, where r and theta are the polar coordinates of z equals x plus iy. So again, theta is measured in radians, and r is equal to the absolute value or modulus of z. And we'll see that this exponential form is very useful when multiplying complex numbers. When we first write complex numbers in exponential form and then multiply them together, we can just use properties of exponents and simplify these expressions. Let's look at an example of exponential form. If I let z be -1 minus I, then the absolute value of z would be the square root of -1 squared plus -1 squared, which is the square root of 2. So this is going to be r in the exponential form. And we already showed that the principal value of the argument of z is -3π/4 in a previous example. So therefore I can represent z in exponential form as square root of 2 e to the I times -3π/4. And there's an infinite number of representations of z in exponential form because we have an infinite number of representations of theta, so we could write z as square root of 2 e to the I negative 3 pi over 4 plus any integer multiple of 2 pi. So any one of these representations where n is an integer would give us the exponential form of z. Let's look at one more example for the number z equals negative 1. Well, the principal value of the argument of negative 1 is pi, and the absolute value of negative 1 is 1. And so in the exponential form z equals r e to the I theta, we get that negative 1 is equal to 1 times e to the I pi. And by adding 1 to both sides of this equation, we get the beautiful identity called Eulers Identity. We have that e to the I pi plus 1 equals 0. And we see that this identity links 5 of the most fundamental math constants: the exponential e, the geometric constant pi, the imaginary unit I, and then the additive and multiplicative identities 0 and 1. Further, it links 3 of the basic arithmetic operations: addition, multiplication, and exponentiation. For another example, let's let z represent a complex number of the form e to the I theta. So the value r of this expression is 1, so we see that this point lies on the unit circle. That is, the circle centered at the origin with radius 1. So if I look at all points of this form, they would all fall on the unit circle. So if this is z equals e to the I theta, where the value theta would be this angle measured from the positive real axis to the vector pointing at z equals e to the I theta. So since e to the I theta lies on the unit circle, we see that the absolute value of e to the I theta must be 1. And we could also write this in rectangular coordinates: cosine of theta plus I sine of theta, to also show, just by using the definition of absolute value of a complex number, we have that this equals the square root of cosine squared plus sine squared of theta. And by the Pythagorean identity, cosine squared plus sine squared equals 1. So we see that the absolute value of e to the I theta is always equal to 1. Now let's look at the conjugate of z. So if I reflect z across the real axis, I'll end up with the point here in the lower half plane. And we see that the argument of z bar will actually be negative theta. And so we get this fact that the conjugate of e to the I theta is actually e to the negative I of theta, because the argument is just going to be equal to negative theta. Let's look at some complex numbers lying on the unit circle. The imaginary unit I can be represented in exponential form as e to the I pi over 2. That would be the argument of I. The real number 1, the principal value for the argument of 1 is 0. This won't give us a useful expression for 1 in exponential form. So I'm going to use 2 pi for the argument of 1. So I could write 1 as e to the 2 pi I negative 1 I can write as e to the pi I. I could write negative I as e to the 3 pi I over 2, or I could write it as e to the negative pi over 2i. Next, let's look at an example that shows that exponential form of a complex number is very useful for multiplication. So let's find an expression for 1 plus I to the power 100. Let's simplify this expression. Well, let's write 1 plus I in exponential form. 1 plus I has radius square root of 2, and the argument of 1 plus I would be pi over 4. So I can write 1 plus I as square root of 2 e to the I pi over 4. I'm going to raise this to the power 100, and we can just use exponent rules. And so we have the square root of 2 to the power 100 would be 2 to the power 50. And then e to the I pi over 4 raised to the power 100 would simplify to e to the 25 pi I. 100 divided by 4 is 25. And then from the previous line, we see that e to the 2 pi I is equal to 1. So I can really just cancel factors of e to the 2 pi I until this expression simplifies to 2 to the power 50 times e to the pi I. But e to the pi I is negative 1. So this would simplify to the real number, negative 2 to the power 50. If we tried to multiply out 1 plus I to the 100, we could use something like the binomial theorem to simplify that expression, but rewriting this in exponential form first and then using exponent rules greatly simplifies the multiplication. So in fact, complex multiplication can be best understood by writing the complex numbers in polar coordinates. So if we have two complex numbers z1 times z2, if I write them in exponential form first, r1 e to the I theta 1 times r2 e I to the theta 2, then when I combine these two expressions, I'll get r1 times r2, and then e to the I theta 1 plus I theta 2, and therefore the exponential form of z1, z2 is r1, r2, e to the I times the quantity theta 1 plus theta 2. And we see that if we multiply z1 times z2, then the radius of the product is going to be r1 times r2. So the radius gets dilated by the factor r2. And then the argument theta 1 is combined with the argument of z2, which is theta 2. And we see that that's going to correspond to a rotation by angle theta 2. So if z is a non-zero complex number, then multiplication by z corresponds to a dilation by the factor absolute value of z and a rotation by the argument of z about the origin. So we see from this previous calculation that if we have the theorem e to the I theta 1 times e to the I theta 2 will equal e to the I theta 1 plus theta 2, and for any integer n, we have that e to the I theta raised to the power n will just equal e to the I n theta. Now, these are just common exponent rules, but we see that when we write this in polar form, we have actually a very useful identity. And this in polar form is called de Moivre's theorem. Or de Moivre's formula. And it says that cosine of theta plus I sine of theta, all raised to the power n, is equal to cosine of n theta plus I sine of n theta for any integer n. So this expression is very useful, especially when you consider very large powers of n. Multiplying out the expression on the left-hand side would be very tedious using all these trig identities. This can be a very powerful simplification. So let's look at an application of de Moivre's formula. So let n equal 2, and we get the expression cosine of theta plus I sine of theta, the quantity squared, is equal to the cosine of 2 theta plus I sine of 2 theta. So when I multiply out the left-hand side of this expression, I will get cosine squared of theta minus sine squared of theta plus 2I cosine theta sine theta. And that will equal the complex number cosine of 2 theta plus I sine of 2 theta. In a previous lesson, we learned that two complex numbers are equal precisely when their real parts are equal and their imaginary parts are equal. So then by equating the real and imaginary parts, we obtain the familiar trig identities. Cosine of 2 theta equals cosine squared of theta minus sine squared of theta, and sine of 2 theta equals 2 cosine of theta sine of theta. So given a coordinate plane, let's look at the unit circle written in exponential form. So the unit circle is the circle centered at the origin with radius 1. Then any point on the unit circle can be represented as e to the I theta. Now let's look at expanding this circle to any radius, capital R. We see that any point in this circle can be represented by the expression r e to the I theta, where the radius is capital R. So this large circle has equation absolute value of z equals r. So then the parametric representation for the circle is the equation z equals capital R e to the I theta, and we let theta go from the value 0 to 2 pi, and vectorially we see if we start out with a vector at argument 0, then as theta goes from 0 to 2 pi, we see that the circle is going to be mapped out once in the counterclockwise direction. And so we see that this is the parametric representation for this circle. Now, more generally, we had a circle centered at z0 with radius r. Then we can represent in rectangular coordinates as absolute value of z minus z0 equals r. Then we can add z0 to the parametric representation of the previous circle centered at the origin. So this has parametric representation z equals z0 plus capital R e to the I theta. Greater than or equal to 0, less than or equal to 2 pi. And so we see that as the parameter theta goes from 0 to 2 pi, the point z traverses the circle once, in the counterclockwise direction.